Good evening, students. I am Matt Belcho, Assistant Professor of Electrical Engineering Department of BSA Crescent Institute of Science and Technology. And here I am going to explain some of the assignment problems which I had already sent to you. So you are able to see the questions of the assignment 2, and it contains part A and part B. I hope you can solve this part A questions, and I'll be spending some time on part B questions, and I may not completely solve the problems, but I'll just explain how you have to go ahead with the problems, maybe some hints and help to solve those problems. So as you know, this part B has got first order system and problems on first order system, second order system, and there are some problems on steady state error and error constants, and there are some other problems on PID controller, use of PID controller. Then we'll be moving on to frequency domain analysis, and first to start with the correlation between the frequency domain and time domain analysis. And also we'll be seeing some problems on frequency domain plots, namely Bode plot and Nyquist plot or polar plot. Okay, so this is the overview of the assignment problems, and we'll just have a look at some of these problems which I think you may find it difficult to solve, or maybe to start with you will find some kind of difficulty. Okay, so here I am going to take the first problem, the first order system problem, that is problem number 1 of part B. So as you know, it is a mechanical system, simple mechanical system. So it has got a mass. So you can draw the free body diagram. So f of t is the input, and of course the reaction forces. There are two reaction forces, one due to mass and another due to the friction. So I can write the equation as f of t is equal to Fm, I mean the reaction force due to the mass and reaction force due to this B. So only thing here is, if you look at the problem, so two different variables are given. Simultaneously you can have a look at the assignment sheet. So find the displacement x of t as well as velocity v of t. Okay, so therefore you have to write this Fm and Fb in terms of both these quantities. I mean, for example, Fm is equal to dV by dt, where v is the velocity, and it can also be written as m d square x by dt, where x is the displacement. So similarly, Fb can be written as there is a small problem. it has gone, so no problem, we will start from the beginning. Okay. So this is problem number 1. F of t equal to m d square x by dt, and if b is equal to b equal to b dx by dt. So using this and using the free body diagram, I can write it as f of t is equal to fm plus fb. Now I can use velocity as variable in one equation. So for example, f of t is equal to m dv by dt plus b into v. Okay, so this is one equation you can say, and the other equation I can write is f of t is equal to m d square x by dt square plus b into dx by dt. So this is second equation. So I can transform this to Laplace domain. The first equation gives me f of s is equal to s v of s plus, sorry, there is one m missing here, okay, b v of s, and this will result in, so this is the Laplace transform of this, and this f of s m s square x of s plus b s x of s. All right. So now I will start here. The first Laplace transformed equation will give me an s v of s by f of s is equal to 1 by output variable is v and the input variable is f. So v of s by f of s is equal to ms plus b, and other equation will result, that is where the variable is x, displacement by f of s is equal to 1 by s into ms plus b. Okay, so now the question is, if so these are the transfer functions with variable v and x as outputs, and what is given is an impulse function is given as f of t, that is an impulse function with a magnitude of 6. Okay, so this is what is given. So Laplace transform of impulse input or impulse signal is 1, and therefore the total Laplace transform of this is simply 6. Okay, so this will result in V of s by V of s is equal to 1 by ms plus b into f of s, that is equal to 1 by ms plus b into f of s is nothing but 6. I can write that 6 here. So this is what? So now you can find f of t by taking inverse Laplace transform of this, and in the same way you can find x of t also by taking inverse Laplace transform of this into 6. So please remember that since it has got two factors, this x of s by f of s got two factors, that is s and ms plus b. You have to do a partial fraction of this, okay, and then you have to take an inverse Laplace transformation. And the last part of the question is find the time constant and final steady state displacement and velocity. Okay, so if you want to find out the time constant, this you can write this transfer function, you can write it in time constant form, that is 1 by, what is the time constant form? The constant should be 1. So therefore here the constant is b, you have to take the constant outside, that is 1 plus m by b. Yes. So I can write it as 1 by b, sorry, this is b equal to, okay, so I will write here, this is 1 by b divided by 1 plus m by b. Yes. So this is in time constant form. So you can compare this to k by 1 plus ts, and here the time constant is m by b. Okay, so that is one answer, and the other answer is steady state displacement and velocity. So you have this f of t here, you will get, sorry, you will have v of t, you will have v of t here. Okay, so this is v of s, this is v of s, and if you take the inverse Laplace transformation, you will have v of t. So from this v of t you can put t is equal to infinity. Whatever expression you get here, you can get both steady state value for v of t and x of t. Okay, so the problem number 1 is over. So we will just move on to problem 2. So here a block diagram is given, 1 by s, sorry, it is k by s. Input is, there is an input, there is an output, and this is, okay, E of s, unity feedback. Okay, so this is plus and this is minus. So what you have to do, the question is find unit step response and unit impulse response. Very simple problem. So let me say the closed loop transfer function is g of s is equal to, so okay, so this is the open loop transfer function, right? Not open loop, forward path transfer function. Otherwise, let me say the closed loop transfer function of the system is closed loop transfer function of the system is g of s by 1 plus g of s h of s. So here g of s is k by s and h of s is 1. Therefore, you will have the transfer function as k by s plus k if you do the simplification. Okay, so now this is your transfer function. Maybe you can call it as h of s, which is nothing but the input is given as r of s. Okay. So h of s is equal to, output is c of s. C of s by r of s. So now you can calculate the c of s, which is the output, that is nothing but h of s, r of s. H of s is nothing but this k by s by k. R of s you have to substitute by 1 by s in case of step response, and r of s equal to 1 in the case of impulse response. So r of s is equal to 1 if it is impulse, and r of s equal to 1 by s for step. Okay, so substitute for impulse response, not necessary to have any partial fraction. For step response, you have to take this partial fraction and take inverse Laplace transformation. That's it. So this third problem, it's an electrical network is given. So inductance are L. Okay, so the current here is I of t. So the voltage across this inductance is E EL of t. Okay, so the question is to find out EL of t if the input here is 5 volts and if I have a switch here and if it is connected by a switch here. Okay, fine. So you can write the different equations and form the differential equation and then go ahead as usual. Okay, so first equation is EL of t equal to voltage across any inductance is given by di of t by dt. Am I right? So then this in Laplace transformation can be transformed as EL of s is equal to s L I of s. So that is I of s. I can get some value, keep it there. Now you can use KCL. So if this voltage I keep it as V of t, that is what is 5 volts, V of t is equal to R I of t plus L into d I of t by dt. Okay, so transform this also. V of s is equal to R, you will get it as R is L I of s. So now whatever you got here, you can substitute here. So that will be I of s is equal to E L of s divided by SL. You will get here and substitute, then you can get this transfer function E L of s divided by Vs of s. Go to get it. Now you have to, V of t is nothing but 5 volts, and since it is applied through a switch, it is, you have to take it as a step function with a magnitude of 5. Okay, so therefore V of s, the input is 5 by s. Substitute here in V of s, then you will get an EL of s, take inverse Laplace transform, and you will get a function, you will get EL of t, okay, as a time domain value. Substitute the values of L, R, okay, you will get a function of t. So another part of the question is also plot EL of t and find the numerical value of EL of t at t is equal to 1. The first part is plot this EL of t. Take time in x-axis for different values of t. Just find out what is going to be the value of EL of t, substitute, and you can plot it. Okay, so probably you have the current will be something like this, and you can try plotting this EL of t and put t is equal to 1 and you will get the value. Okay, that's it. And the fourth problem, tau is given, that is 6 seconds, and the initial values and final values are given. Okay, so you are asked to find out the transfer function and also the response in time domain. Okay, so initial value is 0 and final value is 3 units. So initial zero and final value is 3 units. Okay, these are the data given, and also it is given as a first order system. So obviously G of s will take a form of k by 1 plus Ts. Okay, so this is the standard first order transfer function. So since t is given as 6, you can immediately write it as k is equal to 1 plus 6s. So the only problem here is to find out the value of k. So you have to use either the initial value or the final value. See, there is only one variable here, so that is only one data is sufficient. So better use this final value. Okay, so maybe I think the step response, you have to consider a step response that is missing in the problems. Please include that word step response, first order system step response. Okay, so in that case, if I take y of s as the output and x of s as the input, that is nothing but g of s, that is equal to k by 1 plus 6s. Now y of s is equal to g of s into x of s. Obviously, if I take x of s, I mean if I take x of t input as a step input, then x of s is going to be 1 by s. So it is k into s plus 1 by s 6s. Alright. So what is my final value theorem says? You can use the final value theorem. Okay, so that is y s steady state or the final value is nothing but limit s tends to 0 s into y of s. Okay, so if you do that, you will get k limit s tends to 0, this s and this s gets cancelled, and what you will have here is 1 plus 6s. So that is, if I apply the limits, it is going to be k by 1, which is nothing but 3, which is given. So that means k is equal to 3. So now you got the transfer function y g of s, or y of s you got, y of s you got here because k value is known here. Now you can take a inverse Laplace transform after taking the partial fraction for this and taking inverse Laplace transformation. Okay, so this is the transfer function you got by substituting the value of k. The fifth problem will be dealt later, and because it's a bit lengthy and time, I mean we are short of time, and we will see that in the class later. So we will go on to second order system problems. Question number 6. A servo system controlling a motor, the dynamic equation is given as theta dot double dot is equal to, theta double dot plus 8 theta dot is equal to 200 E, where theta is the output position and E error is the E is the error, which is given by 200. E is given by R minus 0.5 theta. Okay. So your dynamic equation will be theta dot plus 8 theta, theta double dot plus 8 theta dot plus 0.5 into 200 theta is equal to 200 R of t. Okay, R of t. So this is a second order derivative term, first order derivative term, and Laplace transform is s square theta of s, okay, 8 s theta of s plus 100 theta of s is equal to 200 R of s. Okay, so calculate the damping ratio, the value of damping ratio, and comment on its performance. Very simple. Okay, so you can find the output by input equal to Okay, so you will get a transfer function. You will have some s square term plus some s term plus some constant term. Okay, so this you have to compare with. So obviously you have got 200 here. So here it will be 8s. Okay, yeah, s is already there. 8s, and this is going to be 100. Okay, so better you compare it with the prototype second order equation, omega n divided by, okay, so you have to compare it with omega n divided by s square plus k omega n by s square plus 2 zeta omega n s plus omega n square. Omega n square is equal to 100. Maybe you can able to proceed. 2 zeta omega n is equal to 8, and so on. You get the values. And of course, see whether the value of zeta is greater than 1 or less than 1. Depending upon that, you can decide what kind of system is that, whether it is underdamped or overdamped or critically damped or whatever. So the seventh problem is a simple problem. Open loop transfer function is given, g of s is given, and damping ratio is also given. Damping ratio is given as 0.5. In that case, you are asked to find out the value of k, peak overshoot, peak time, rise time, and settling time. So all these values can be found if, so it is not delta, it is zeta. Okay. So you can find all the values if you know zeta and omega n. So your task is to find out omega n using the given values. So it is a unity feedback system, but g of s is given. For a unity feedback system, the closed loop transfer function, that is c of s by r of s, is equal to g of s by 1 plus g of s h of s. H of s is unity feedback system. Use this and find out c of s by r of s. Now you will get a second order transfer function. Again, compare this with this prototype system. You have been already given the values. Okay, so zeta is given, omega n is zeta is given. Find omega n and use that to find out k also. You will be able to find, and once you find all these things, you can find all the specifications. It's a simple direct problem. Okay, and question number 8. So here we have a block diagram, second order response. So the question is, determine all the specifications of the second order response for the following system shown in figure 4 when the unit step input is given. The same thing, only thing is g of s is given in a block diagram form. G of s is equal to 100 by s into s plus 12. So in the same way, find c of s by r of s. Okay, equate it to again compare this to this prototype model. We will get zeta. Sorry. You will get zeta omega n. Once you find zeta and omega n, you can find all specifications like TR, TP, okay, MP, TS, TD, all these things. Okay, just find. So that is what is, that's also a straight problem. Okay, so 9. So I think this ninth problem we have already solved in the class. So I am not going to spend much time. So the peak time is given. Question number 9. Tp is given and MP is also given. Use the expression of MP to find theta, then use this in the expression of Tp, get omega n. Okay. So once you find the theta and omega n, just find out the range of the value of theta. So whether in what range it falls, whether it is less than 1 or 1 or greater than 1, see whether it is overdamped or underdamped, and based on the value you have the value for theta, you have the expression for theta, use it and get the expression, that's it. So that is what is 9th. 10th problem. Okay, measurements. Yeah, so the C of t is given here. C of t is given here as 1 plus 0.2 e power minus 60 t minus 1.2 e power minus 10 t. All right. So this is the response for R of t is equal to U of t. Okay, so that is the input. When unit step input is applied, obtain the closed loop transfer function, the damping ratio, undamped natural frequency of oscillations and everything. Okay, so C of t is given. So can you find out C of s? Yeah, you take a Laplace transform of this. One is 1 by s plus 0.2 e power Laplace transform of e power minus at is equal to 1 by s plus a. So use that, s plus 60 minus 1.2 by s plus 10. Okay, so now you can simplify this, you get the transfer, C of s. Okay, so you will have s plus 60, s plus 10, and simplify, you get the numerator. So what is R of s? R of t is U of t, R of s is equal to 1 by s. So now can you find out the transfer function? Transfer function is nothing but C of s by R of s. Both are available, you get the transfer function. So once you get the transfer function, again you can compare it with this and get theta, omega n, everything you can get. So 11th and 12th problems, I think it will not create any problem to you because we have already worked out in class. Similar problems we have already worked out sufficiently, and I am not going to take up those problems. So straight away we are moving on to 13th. Question number 13th. Yeah, so this is also not a big deal. So consider a unity feedback control system with a closed loop transfer function. Closed loop transfer function is given, C of s by R of s. Determine the open loop transfer function first. Show that the steady state error in the unit ramp response is given by this. So what you have been given is C of s by R of s. It is nothing but actually G of s by 1 plus G of s into H of s, but since it is given as a unity feedback system, H of s is 1, so I am not writing it, only it is G of s here. So that is what is given as K s plus b divided by s square plus AS plus B. Okay. So what can you do? So how can you write this? So this you have to get in the form of 1 plus something into something. This polynomial rational expression has to be written in this form. Okay. So convert it. So do some algebraic manipulations here. Write in this form, you will get a rational expression here and here. That is what is your G of S. Okay, that's it. So G of S you get like this. Once you get G of S, once you get C of S, you can find steady state error, right? So it is a just see what the system is, what is the type of the system, and you just find out the error for unit ramp. Unit ramp is ESS is equal to 1 by KV. We know what is KV. KV is equal to limit S tends to 0 S into G of S. All right. So you just get S KV. Then once you get KV, you can put it here and find that expression. You should get it as A minus K by B. That's it. So this is how we have to proceed this. Okay. So 14th problem. Yeah. So figure 6 has three systems. Systems 1 is I'll take up so this is what is the problem. System 1 is proportional. So we use a proportional controller here, and this is with the proportional and derivative control. And the third one is with some other feedback. We have gotten velocity feedback also. This is velocity and this is displacement. Okay. So compare the unit step, unit impulse and unit ramp responses of the three systems. Which system is best with respect to the speed of response and maximum overshoot and in the step response? Maybe at least you can try with step response for all these systems. Just find out the closed loop transfer function of this. For example, in this system, G of S is equal to 5 into this, that is 5 by S into 5S plus 1 is G of S. So use G of S by 1 plus G of S H of S as to find out the closed loop transfer function. Then C, that is closed loop transfer function is nothing but C of S by R of S. Put R of S is equal to 1 by S, you get take inverse Laplace transformation and everything, you find response, step response. Here also you do the same thing. Here also you have to do this. Only thing is here you need to do a little kind of a little bit of block diagram reduction to get the closed loop transfer function, because this loop you have to reduce first and take the other loop together to take the closed loop transfer function. Then apply R of S is equal to 1 by S, just find out C of S, C2 of S and 3C of S. Okay. So for all these systems, you will result, all these systems will result into second order systems. So system 1, system 2 and system 3 will result in second order system. All these systems have to be related to this prototype second order transfer function. Find zeta and omega in for all these systems. Find the what you can do is what you can find is the settling time and peak time. They are the maximum overshoot, settling time and peak time. Get those values, compare and see which has got lower peak overshoot and lower peak time and lower settling time. So that response is the best response. Just find out which is going to give you the better response in that way. Okay, so that is what is your that is what is your 14th problem. Okay, yeah. Then we are moving on to frequency domain. So in the frequency domain, the specifications of a second order unity feedback control system with the closed loop transfer function T of s is equal to this omega n square divided by square plus 2 zeta omega ns plus omega n square, or that the maximum overshoot must not exceed 30% and rise time must be less than 0.2 seconds. Find the limiting values of resonant peak MR and omega B. It's a very straightforward problem. So it is MP, peak overshoot is 30% or 0.3. Use that value to get zeta. Rise time value you can maybe from the rise time expression equate it to 0.2 and get omega n using this 0.2 and zeta value whatever you get it from peak overshoot. Then substitute those zeta and omega in MR and omega B expressions. You get these values directly. That's it. 16th. Yeah, bandwidth, it's reverse. You are coming back. Bandwidth is given. Phase margin is also given here. And we have expressions for bandwidth and phase margin in terms of zeta and omega n. So you get those, substitute and get those values of zeta and omega n. Using those values, get back the time domain values like TP, TR, all these MP and all. Okay, so that's it. These are all very, yeah. Maybe I'll complete with explaining one more problem. Right. So 17th. So the Bode plot is given. So this is the Bode plot. Okay, so the Bode plot is given. So you have to find out some of these specifications of this: gain crossover frequency, phase margin, phase crossover frequency, gain margin, cutoff frequency, bandwidth, resonant peak and resonant frequency. Okay, so yeah, the first case is gain crossover frequency. Gain crossover frequency is the frequency at which the gain becomes 0 decibels. So 0 decibels comes here and the frequency corresponding to this is the gain crossover frequency. And phase margin is the margin available at this. So straight away you have to come here in the phase plot. What is the angle? It is maybe around almost minus 140 degree. So it is 180 plus this minus 140. So the phase margin is 40 degree. Okay, so then phase crossover frequency, the frequency at which the phase becomes 180 degree, it is 4 radians per second. Gain margin, gain corresponding to that particular frequency is 4, right? Here it is 4, and for that 4 it is minus 6, and therefore your gain margin is 10. Gain margin is 10. Okay, so you got 10 decibels to reach 0. Okay, so that is your gain margin. And cutoff frequency 0.3 decibels down. So this is 0.2, almost at 0.3 decibels you have to draw a line. So this is the corresponding cutoff frequency. If I draw a line as minus 3 decibels, this is going to be the projection, this is what is going to be the corresponding cutoff frequency. Okay, so then bandwidth, so here is we have got only one cutoff frequency. So within this region, okay, this part, the gain is high and therefore that becomes the bandwidth. I mean all the frequency range lesser than this cutoff frequency is your bandwidth. And resonant peak, I don't see any resonant peak in this because there is, it's okay, and resonant peak and resonant frequency may not be valid for this Bode plot. So you should be able to see some kind of peak, okay, rising, then only you will be able to get resonant peak and resonant frequency, resonance. So we don't have those values. So these polar plot and Bode plots have been well discussed in the class, so I am not covering them. So hope you understood to some extent, you understood the concepts behind these problems, and I think you will be able to solve and you can get the answers. Thank you. Please do the exams well. All the best. Thank you.